Hello, my name is Nathan Hadaway, and this is my Physics 2211 Lab 4 lab report on oscillations. So what is this lab? Well, this is a lab where we took a mass of about 0.402 kilograms. We attached it to a spring with a spring constant of 6.83 newtons per meter, and so one side of the spring is attached to the mass, the other side of the spring is attached to a pivot above the mass, and then I moved the mass in the negative x and positive y directions so that it oscillated side to side like a pendulum, but also up and down like a spring. And the initial position that the mass was set to was negative 0.120 and negative 0.656 meters for the x and y positions. That's setting the axis of the origin to be the place where the spring is pivoting. So it's like the top place of the spring, the place where the spring ends, that's not connected to the mass. So the first thing I did was I took a video of this mass moving through the air, and I tracked its position. Second thing I did was I tried to simulate the exact same thing in a glow script in code, and use the exact same initial conditions as the real world. And obviously, if I used all the right equations and used all the right initial conditions, then the information, the data collected from the real world and the simulation should be the same. If they are the same, it proves that the equations that I used in the simulation are basically the equations that I use in real life. They're accurate equations, right? You can see some of those equations that I use to solve for kinetic energy, gravitational potential energy, and spring potential energy in the bottom right-hand corner. Also, if you're curious about any of the rest of my glow script, you can look at the URL there below that, the HTTPS, and then jumble of letters after that. The final thing that I did was I compiled the data that I got from the real world and from the simulation, and I saw if they were the same or at least similar. What is the lab trying to prove? Well, it's trying to prove a few things. First off, that this mass is only being affected by the only energies that are changing throughout time are kinetic energy, gravitational potential energy, and spring potential energy. These are the same three energies that I showed on the slide before. If these are the only changing energies in the system, then because those are the only ones that my lab took into consideration, then my lab should be basically should be accurate, should be the same as the real world data. It is also trying to prove that the surroundings are not um, are not doing any work on the system. So there's no energy being added or taken out of this system by the surroundings, and this would be shown by the fact that the change in energy is constant, as you can see in the right hand bottom graph. Delta E, the orange line, stays constant throughout time, meaning that there's no work being done on the system. It is also proving that pendulums and springs are harmonic motion and give a sinusoidal kind of motion and force. So this is the data that was collected, blue being the data from the simulation and red being from the real world. Some assumptions I made while coding was that, again, there's no forces acting on the mass, there's no work, or I guess more accurately, there's no work being implemented upon the system. And so, the change in energy is zero. Some possibilities for error that show discrepancies between the real world data and the simulated data. Those can be from, as you can see, there's quite a big discrepancy in the y position graph of about 10 centimeters. And this is because when finding the position of the mass, I used the center of mass of the mass, right? But the simulation simulated from the end of the spring, which is about a 10 centimeter difference, and shows the discrepancy in the y position. Other reasons for error could be that I don't have an infinitesimally small delta t, meaning there's always going to be some rounding error in the simulation. There's also could be human error because I didn't exactly select the center of the graph, things like that. Some frequently asked questions are, is the energy principle satisfied? And I touched on this a little bit earlier, but yes, the energy principle is satisfied because the energy principle basically says the change in energy is equal to the work plus the Q, the change in thermal energy of the system. And this is true because work and Q are zero, so we should expect that the change in energy should be zero, which is what we see. As you can see, the orange line on the top right-hand graph stays constant, stays zero. Energy principle satisfied. Now, what are the periods of the x and y directions? Well, I calculated the periods of the x and y directions to be about 1.69 seconds and 1.47 seconds, respectively. And it makes sense that they'd be different because in the x direction, the period should be in relation to to a pendulum, right? So the period would be 2 pi times the square root of m over, or my bad, in the sorry, in the x direction, it should be the period of a pendulum, which is 2 pi times the square root of L over G, whereas in the y direction, it would be the period of a spring, which is 2 pi times the square root of M over K, which is why we see the discrepancy in oscillations. Thank you for listening.